So, as I told you guys, today we finish these exercises, and then if you still have time at the end of the lecture, if you have additional questions, you can ask me. Otherwise, you can ask me all your questions tomorrow. Tomorrow I will do an exercises on your request, and maybe if you have not enough requests, I can also decide to I can solve some of the exercises contained in the simulation in the mock exam, I mean. As I told you, only to continue to talk again and again. Yesterday, you see, I uploaded in the chat a new folder called Simulations 21-22. I simply, as I told you this morning, I simply checked, corrected some typos present in some of these simulations from A to H. Then I added 2 additional simulations created yesterday, simulation I and simulation L, and to simulation I and L are associated to Excel file. But okay, I'm simply talking in order to arrive at a quarter to 2 p.m. Then at a quarter to 2 p.m. we will start by doing the exercises. And tomorrow, I repeat, yesterday a student wrote me asking to do the simulation the 20, but I told you, as I told you, talk. The students that are present at the lecture can talk, and then tomorrow we will establish the exam date. Okay, and I will tell you all the exam rules, everything. So you don't need to write me. Tomorrow we will discuss everything. If I forget something you believe is relevant, you can ask me. Okay, so tomorrow we will ask. Then everything will be recorded as always, so everyone can get access to the same informations. So now, guys, it's time. It's time to start. Okay. So, guys, table, no. So I go about. So I opened again the file about the simple linear regression model. We finished the theory before lunch, and so now we can do exercises that requires the application of the things that we saw together this morning. Okay, exercises. So now let me see. Okay, these exercises are very important because for sure I will give you an exercise on the exam containing this topic. Okay, so we are only 13, but okay, we need to start because we started later as I told you this morning, but now really we need to start. So exercise. A large company that owns a chain of stores located in different Italian cities wants to assess the impact had by an investment in advertising made in the month of September. To this end, it selects, this company, a sample of 20 stores located in towns similar in population size and other characteristics that may influence the buying behavior. So for each stores are detected investments in advertising, volume of sales between September 20 to November 30. The analysis produced the following results. And here I reported some computation. Remember, which are the variable of interest are the variable X, which represent the investment in advertising, and Y, the volume of sales. So a sample of 20 stores have been selected, and for this sample of 20 stores were measured both the investment in advertising and the volume of sales between September 20 and November 30. The analysis produced these following results. So this computation has been already made. So this is what? The sum of the cross product between advertising expenses and sales for each of the 20 stores. Then the sum of the squares, the sum of the squares of the y. Then here a small x bar has been computed. So this is the estimated average investment in advertising, and small y bar is the average volume of sales for these in the sample made up by these 20 stores. Now, question A. Quantify the linear interdependence. What does mean that we need to quantify the linear interdependence? Which is the measure of the linear dependence? Is the correlation. So to quantify the intensity of the degree of linear relationship between the advertising expenses X and the sales Y in our sample of data, we need to compute the sample correlation coefficients. If you remember, the sample correlation coefficient can be either computed as the ratio between the sample covariance and the square root of the product of the variances, or alternatively, it can be computed as the ratio between the codeviance, the sample codeviance between X and Y, and the square root of the product of the deviances. Okay, so it's similar computation. However, now to compute the covariance, therefore, to the correlation, which is rho hat XY, the empirical correlation, the sample correlation, what do we need? We need to compute either the covariance or the codeviance, the variances, or either the the deviances. Which information do we have here? We have the sum of the squares and we have X bar. So for example, we can compute immediately the deviance, sample deviance of the advertising expenses, X, and the sample deviance of the sales. Remember that the deviance is the numerator of the variance. Given this information, what can we do? We can do the sum of the xi square minus n, which is the dimension of the sample, times x bar to the power 2. Okay, I reported everything here. So we have already this sum. Okay, this is the deviance, okay, of x. So we have this sum. How many, which is the dimension of the sample? We have 20 stores, so 20, and so minus 20 times x bar raised to the power 2. So x bar was this one, raised to the power 2, and this is the deviance of the advertising expenses. Now, in the similar fashion, we can compute the deviance of y. The deviance of y, again, is the sum of the squares minus n times y bar, the sample mean of y, raised to the power 2. Okay, so the sum of the square is reported above. N is 20 again, y bar is the sample mean of the sales, is reported above, and this number must be raised to the power 2. So I simply inserted into the formula the data I provided. And so this is the deviance. So we have this one. We have this one. To compute the correlation, we still need the codeviance. Okay? Which is the codeviance? Well, the codeviance, how can we compute it? Do we have enough information? Yes, because you see we have the sum of the cross product. Remember, the codeviance can be computed as, according one of the two formula I gave you, is the sum of the cross product minus n times the product of the averages. So go below. You see the sum of the xi. So we have this number, which is this one, minus n, 20, the sample mean of this advertising expenses times the sample mean of the sales. So if you do the computation, you get this result. Obviously, guys, If you want to compute the covariance, how can you do? Codeviance, which is this one, divided by 20. If you want to get the sample variance, divide the deviance by 20. If you want also this sample variance, the sample variance of y, deviance divided by 20. Okay, but we don't need that. At least at the moment, we don't need them. So we can do codeviance, which is this one, divided the square root of the product of the deviances, this times this. And this is exactly what I wrote here. So if you do the computation, you get 0.96. Which is the interpretation of the correlation? What can you say, guys? Because you must be able to interpret the result, especially if I ask it to do it. What we can say that there is a really strong degree of linear dependence between advertising expenses and sales for the 20 analyzed stores. In particular, there is a positive degree of linear dependence, and specifically, the degree of linear dependence is the 96% of the maximum possible degree of positive linear dependence, because 0.96 is the 96% of 1, and 1 is the maximum theoretical degree of positive linear dependence. So you see, we have that the degree of linear dependence is the 96% of the maximum positive degree of linear dependence. So it's really, really, really strong, really, really strong. However, the correlation tells you nothing about the direction of the dependence, because correlation of xy is equal to correlation of yx, is a symmetric measure. Okay, so we know nothing about the direction of the dependence, because this is in both directions. Okay. Then second question, express the sales as a linear function of the advertising. Express the sales as a linear function of the advertising investment and estimate the slope and the intercept of the regression line. So express the sales as a linear function of the advertising investment. So obviously the independent variable is represented by the advertising investment, and the dependent one is y, which is the sales. It does make sense to study the sales as a function of the advertising expenses and not vice versa. And estimate the slope and the intercept of the regression line. So here is the model that we want to estimate. yi, which is the sales of the ith store, which is in general random variables given by beta 0 plus beta 1, xi, the advertising expenses of the ith store, plus epsilon I, where again epsilon I is our error term, which is a random variable, etc., with expectation 0, variance sigma square, which is constant for I equal to 1 to n. So what do we want to do? We want to estimate the model. So what do we need to get? We know that the two estimators are the OLS estimator of the intercept and of the regression coefficient. So which is the formula beta 0 hat? Remember, is y bar minus beta 1 hat times x bar. This is an estimator. After having inserted into y bar, x bar, the observed data, you get an estimate, which is a number. You see that in order to compute beta 0 hat, you need the arithmetic mean of y, we have it, the arithmetic mean of x, we have it, but you need also beta 1 hat. So therefore, it is fundamental to compute first beta 1 hat. Beta 1 hat, if you remember, is the covariance between x and y divided the deviance of x, or divided the variance of x, or alternatively, the codeviance divided the deviance of the regressor. Since we have already computed the codeviance in the previous step and also the deviance, we can do simply codeviance divided the deviance of x. These numbers are reported in point A, in the first point. So we got that beta is 2.29. Now look what you have to do. Now you have to no, look, there is nothing to see. You have simply to take 2.29, put it here. Here put the average of the y, here the average of x. So I simply inserted the number, do the computation. Okay, now I didn't ask to do it, but to review, we want to provide an interpretation of the estimates. Which is this one? This is an estimate of beta 1. And which is the meaning of this number? This means that if you increase by 1 unit the advertising expenses, so X, if you increase by 1 unit, by €1, the advertising expenses, you expect on average an increment of the sales of €2.29. But this is not the true increment, is the estimated increment. The estimated increment, okay, is the estimated increment. So if you decrease by 1 unit the advertising expenses, you expect a reduction of the sales of about €2 minus €2.29. Which is the meaning of beta 0 hat? Remember the interpretation, we studied a lot of interpretation already in the first lecture. Which is the interpretation of beta 0 hat? Is the estimate of the intercept. So is the estimated value of the variable y when x is equal to 0. So in our specific case, we say that the volume of sales for a store having no advertising expenses is about 7.73. So I think these are thousands of euros. So the sales, the expected volume of sales for a store with no advertising is approximately equal to 7,370 euro or dollars, depending on the unit of measure. So which is, guys, the estimated regression line? Well, remember the estimated regression line is y hat I equal to beta 0 hat plus beta 1 hat xi for I equal to 1 to n. So which is the estimated straight line? You have simply to insert into beta 0 hat and beta 1 hat the estimate you got here. So this is the estimated straight line, and this straight line can be used, for example, to perform forecast. But okay, this is the estimated straight line. So you see that when xi is equal to 0, this term disappears, and you have that y hat I of a store with 0 advertising expenses is effectively beta 0 hat. Then another question, the following question is the following. Evaluate the goodness of the fit of the linear model. Here I answered to the question in 2 different ways. Already from the first lecture, but we proved it also already today, we know that when you work with a simple linear regression model, the goodness of the fit, which is obviously the R square, capital R square, is equal to the correlation coefficient raised to the power 2. So the quickest way to solve this, to answer this question, given the information we have, is the computation of the R square as the correlation coefficient, okay, sample correlation raised to the power 2, because we have already computed the correlation coefficient at point A, and we got 0.96. So the simplest and most quick to do is simply to take the correlation coefficient, raise it to the power 2. So we got 91%. So which is the explanation of this result? This is a measure of the goodness of the fit of our model to the data. In particular, this means that the 91% of the variability of the sales in the 20 stores analyzed can be explained by its linear dependence with the advertising expenses. In other terms, our model, our estimated model, is able to explain the 91% of the variability of the sales, which is very good, very huge, because remember the R square can assume value between 0 and 1. Alternatively, guys, we can compute, but since these exercises are useful to study, to review, so I computed the R square also in another way, because which is the general definition of the R square, which is always true, is the explained sum of squares over the total sum of squares. That is the deviance of regression over the total deviance. The total deviance, total sum of squares, is the deviance, sample deviance of y. So for the reason you have a hat always, deviance of y. Okay. And then the explained sum of squares, I've shown you this morning, that can be computed either as beta 1 square hat times the deviance of x, or alternatively and equivalently as beta 1 hat times the codeviance of x, y. So here, for example, I selected beta 1 square, deviance of x, deviance of y. So we estimated in point A both the sample, computed in point A both the sample deviance of x, the sample deviance of y. So, and here are their values. Furthermore, in point B, we estimated the regression line, and we find out that beta 1 hat, the estimate of the slope of the regression line, is 2.29. So put here 2.29 and raise to the power 2. If you go do the computation, obviously you get the same result. In the exam, it depends. It depends on the information you have. Sometimes you can compute this one. It is convenient to compute this one. Sometimes it is convenient to compute this one. Sometimes I also ask you to compute the R square in two different ways. It depends. So you must know both methods, okay? Estimate the variance of the error. If you remember, which is the variance of the error? Remember that the assumption about the linear regression model is that the variance of the error for I equal to 1 to n is constant and is equal to sigma square. So in other terms, we want to estimate sigma square. Remember that this morning I talked a lot about this estimation. Okay, and remember that I told you that, and I explained why, in this case, the variance of the error is estimated by considering what? The ratio between the deviance of the residuals over n minus how many parameters do we have to estimate in the regression line? Beta 0 and beta 1. So n minus 2 degrees of freedom. In other terms, okay, now I show you. Deviance of the residuals divided n minus 2. The deviance of the residual, because I told you that these terms are all very important, can also be computed called as residual sum of squares, because it's simply the sum of the squares of the residuals, divided n minus 2. Do we have any information that allow us to compute the residual sum of squares? Remember that I told you the residual sum of squares is the sum from I equal to 1 to n of the residuals, of the squares of the residuals. Do we have this information in the data above? No, we do not have this information, so we cannot compute it directly. However, this morning we studied a very important topic, I told you, which was the decomposition of the deviance. The decomposition of the deviance, if you remember, tells you that the total sum of squares is equal to the residual sum of squares plus the explained sum of squares. So the residual sum of squares will be obviously the total sum of squares minus the explained sum of squares. But what does mean total sum of squares? Is the deviance, the sample deviance of the y. So we have it. Minus explained sum of squares is the deviance of regression. We computed it in the previous step. Remember, it's beta 1 hat square deviance of x. This has been computed here in this numerator. Okay, this is the deviance, ESS. TSS, we have both. So RSS, the residual sum of square, is TSS, this one, minus ESS, this one. So is 203,92 minus this numerator, which is this one. So substitute the data. Okay, you say substitute the data. The number of observations are 20 minus 2 is 18. Do the computation. and you get 0.9759. So this is the so this is an unbiased estimate, of the variance of the error. Okay. So this is the variance of the residual, which is an unbiased, and this provides an unbiased estimate of sigma square. So S hat square is an unbiased estimator of sigma square. After having inserted the data, you get an estimate. But this, as I told you, is an unbiased estimator of sigma square. Now, another point. Assume the errors are normal. So the epsilon I are normal. Find the confidence interval for the parameters of the model at the confidence level 95%. So what do we need to do, guys? Well, here we need to perform, to build confidence interval for the parameter beta 0 and for the parameter beta 1. We showed this morning how easy it is to build a confidence interval. In particular, guys, we saw two cases, the case in which the errors are normal and the case in which you can say nothing about the distribution of epsilon I, but the dimension of the sample is huge. So, but here you see we are in the case that the errors are normal. So in this case, you should remember, I mean, if you don't remember, okay, I wrote it here, that the reference distribution in this case is the student's t distribution with n-2 degrees of freedom. So if you go back, if you look at the table I prepared, yes, we have that we are exactly in this case, is beta 0 hat plus minus what? Guys, we need to build the confidence interval at a confidence level 95%. So 1 minus alpha is 95%, alpha is 5%. You need to find two values on the table of the t, so you have to divide alpha by 2. So 5% divided by 2 gives you 2.5%. So we have plus minus 2.5% of what? How many degrees of freedom? N minus 2. So 20 n minus 2 is 18. So to find this value, we have to go on. We have to use the table of the student's t, and we will do into a moment. Times what? The standard error of beta 0. I told you don't need to remember the formula of the standard error, because either I provide it during the exam, or alternatively I simply tell you which is already the value of the standard error. So this is the standard error of beta 0. Let me see. Yes, it's correct. Square root of s at square 1 over n plus x bar square divided the deviance of x. So here, to build the confidence interval, therefore, you see, first of all, I inserted here beta 0 hat, which has been estimated at point B, okay, is the estimate of beta 0, which is this one. Then minus plus or plus minus, what? We need to take the table, and in a moment we will do it. But first I want to compute this one. So is square root of what? S hat square. S hat square has been computed before, is the deviance of the residuals. Sorry, the variance of the residuals. This one. Parenthesis 1 over n. How many? Which is the dimension of the sample? 20. N equal to 20. So divided by 20 into x bar. Put the observation, put your mean, we have it, is the data provided by the text, raised to the power 2, we computed already the deviance of x, the sample deviance, so put it inside your number, and this is the standard error of the estimator, which is a measure of the variability of the estimator around the mean, its mean. So we have this number, we need now to find this value by using the table of the student's t. So table 1, no, I think it's table 3. Yes, table 3 percentiles of the student's t random variable. So we want to find the value of the student's t with 18 degrees of freedom, such that the amount of probability is alpha over 2. But as I told you, alpha is 5%, alpha over 2 is 2.5%. So 2.5%. Remember that this number here in this row corresponds to alpha, the green area. So we want alpha equal to 2.5%. So this is the column in which we have to look. And how many degrees of freedom? 18. So go below, go below 2.101. So 2.101, 2.101. So this is the percentile we wanted to find. So 2.0, okay, I wrote only 2.1, but should be, to be more precise, is 2.101. Okay, put it here, make one time the computation with the minus, and remember, I wanted to see here in the exam the lower extreme of the interval, and I want to see here the upper extreme. I do not want to see first this one and then this one, okay? First the lower extreme, then the upper one. Okay, and so this is a confidence interval for the intercept built at a confidence level of 95%. So 95% of the sample that we can select will provide a confidence interval containing the true mu. So there is only a chance of 5% that our confidence interval will not contain the true mu, the true beta zero, because there is a chance of 5% that we selected that sample, but we cannot know if this is a good sample or a bad sample. However, we know that 95 over 100 samples are good, and only 5 contain misleading information. So this is the confidence interval for beta 0, which for beta 0, no beta 0 hat. Beta 0 hat is an estimate. We are interested in beta 0, which is unknown. Okay, so for beta 0, confidence interval hypothesis testing concerns parameters, unknown parameters. Okay, so don't do this mistake. Okay, now we want to build a confidence interval for beta 1. Again, the formula is easy to remember because you have beta 1 is always plus the value you can find on the table of the student's t times its standard error. The standard error of beta 1 hat, I told you that you don't need to remember, is square root of s hat square divided the deviance of x. We computed the variance, s hat square is the variance of the residual. We computed it. Deviance of x has been also computed. Insert your data here, here, and here, and this is the standard error of beta 1 hat, which is a measure of the variability of the estimator beta 1 hat around its mean. So you see the variability is not great around its mean. Okay, how can we build now the confidence interval? We have all the information because we substitute into beta 1 the estimate 2.29, which has been computed at 0.2, plus minus or minus and plus. What is the critical value? The critical value is the value. You find it again using the student's t with 18 degrees of freedom. The confidence level is always 95%, so alpha is always 5, and alpha over 2 is always 2.5%. So we don't need to take again the tables because we find out the value previously is exactly 2.101. Okay, this number times the standard error. Again, do the computation first when you have the minus and you get the lower extreme of the interval, then with the plus and you get the upper extreme of the interval. So this is a confidence interval for who? For beta 1. Beta 1. So there is a chance of 95% that the sample we selected is a good sample, so that the interval we built really is an interval that really contains the true beta 1. But there is still a risk equal to 5% that we selected a bad sample, and therefore that the interval we built does not contain the true beta 1. Okay, then I asked you a question. Are the parameters beta 0 and beta 1 significantly different from 0 at a tail probability level of 1%? What does this mean? This means that we need to perform two hypothesis testing. One system of hypotheses concerns beta 0. So, what does mean significantly different from 0? That under the null, we will have beta 0 equal to 0, under the alternative beta 0 different from 0. This is the first test we need to perform. Then another test would be beta 1 equal to 0, under the alternative beta 1 different from 0. And the tail probability level is 1% for both tests. So we start with this one. As I told you, explained this morning, we have that the statistic test, in this case, guys, the errors are normal, so we are in case A, and we know that under the null, this statistic test follows exactly a student's t with n minus 2 degrees of freedom. Okay, so is beta 0 minus the value for beta 0 under the null divided the standard error of beta 0. So, but under the null for us, beta 0 is equal to 0. So this is our statistic test. It's simply beta 0 hat divided the standard error of beta 0 hat. Before selecting the sample, remember, this is a random variable. Was distribution under the null, which is an exact distribution, is a student t with 20 minus 2 degrees of freedom with 18 degrees of freedom. So what do we have to do now? Nothing difficult at all. We need simply to compute the observed value of the statistic test. Then we need to find, since the alternative is bidirectional, two critical values on the table of the student's t with 18 degrees of freedom. So here I follow what I did. I computed first the observed value of the statistic test. You see that it's immediate. Beta 0 hat has been estimated, was 7.37. SE beta 0 has been computed in the previous step when we build the confidence interval, the standard error of beta 0. So I substitute, and the observed value of the statistic test is 12, etc., etc. What can we say? We need to establish if beta 0 can be considered equal to 0 or not. At a significance level, 1%. Alpha is 1%, guys. Alpha is 1%. Alpha is 1%. So alpha over 2 is 0.5%. So we need to find two values on the table of the student's t with 18 degrees of freedom. Okay, in particular, 0.05% is essentially, no, it's essentially, is 0.005. So take the table. We need to find the percentile of a student's t with 18 degrees of freedom such that the green area is exactly 0.005. You see, so we are in the last column. Now you have to go below until you reach 18 degrees of freedom. So here you see 18 degrees of freedom. So the percentile or critical value is this one, 2.878. So remember that the student's t is symmetric. So you have two critical values, and the other one is simply the same, but with the sign minus. Okay, so we have two critical value minus this number and plus this number. So let me. Okay, these are the critical values. Now ask yourself, is this number inside this interval? The interval extreme -2 blah 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 and +2 blah blah blah? No, is very huge number, is really outside of this interval. So what does this mean? This means that at a significance level of 1%, we reject H0 in favor of H1. So what does this mean in practice? This means that we believe that the intercept of the model is significantly different from 0. Okay? What does this represent, guys? In our model, what does beta 0 represent? The level of sales when the advertising expenses are null. So so essentially we are establishing that a shop or a store, even without making advertising, has a positive volume of sales. So this is essentially what we are stating by accepting this, by rejecting H0 in favor of H1. Okay, here there are all the explanation. Now we want to build to test the same hypothesis concerning the beta 1. So the coefficient of regression. Again, the statistic test is similar to the previous one. Beta 1 hat minus, I called it, to be precise with the notation I used, you should write the 1 before the 0, because previously I used the notation with the 1 before the 0. Because essentially, what I mean with beta 1, 0? The value of beta 1 under the null. So I prefer that you put the 1 in front of the 0 and not after the 0, okay? Because I think previously I used beta 1, 0. So means the value of beta 1 under the null divided the standard error of beta 1. Okay, and remember that this result has been provided this morning, and under the null assumption, the distribution of this statistic test is a student's t with n-2 degrees of freedom. In our specific case, beta 1 under the null, that is beta, this is, guys, corresponds to beta 1, 0, the value of beta 1 under the null assumption. We assume that is 0 under the null, so substitute 0 here, and therefore in particular, our statistic test is the following, is this one, which follows under the null assumption, and students t with 20-2 with 18 degrees of freedom. Again, what you need to do, you have to compute the observed value of the statistic test, and you have to compute it with the two critical values. So we have already computed beta 1 hat and the standard error of beta 1 hat, so we simply have to insert previous data, and we get this number. Now, we need to compare this number with the critical values of the test. But guys, which are the critical values of the test? We need to perform, again, the test at a significance level 1%. So this means that we need to divide alpha by 2. We get 0.5%. So in other terms, the critical values that we need to find are exactly the same reported here. Okay, so we don't need to take again the table. So I simply reported here the same critical values, but as you can see, this falls in outside of the interval having as a stream -2, etc. and +2, etc. So again, we reject H0 in favor of H1. But so which is the meaning? We believe, therefore, that the regressor, which was the regressor? X. The regressor was the advertising expenses. The advertising expenses have really an explicative power to determine the volume of sales of a store. In particular, we really believe that there is a linear relationship between a positive, in particular, linear relationship between who? Well, so for the moment, okay, between what? The sales and the advertising expenses. That is, the sales are positively correlated with the advertising expenses. So, and this is a really linear relationship between the two, an approximative linear relationship between the two. Okay, so you see the exercises are not difficult at all. You have always to study to remember the concept, because if this was the first time you studied it, or if you studied statistics but you copied, or simply you did the exam in which you have to do only exercise mechanically with everything or all the notes with you, maybe you don't remember. But unless you studied already very well statistics, maybe you forget everything. Otherwise, it's simply a short review for you. Okay, but for other people who saw it for the first time, who never studied statistics, who cheated, etc., etc., this is very useful. Okay, so first review the theory studied this morning, then with the theory, look the theory, then do again these exercises. Furthermore, when you know the theory very well and you know this exercise, you can solve everything we did, all the mock exam you can solve. Okay, exercise B, guys. Obviously, if you have troubles, turn on the microphone, okay? Yes?
Could you please repeat the meaning of the result we found regarding beta 0?
Beta 0. Yes, I was saying that beta 0 is the intercept, okay? And obviously, I told you that obviously the intercept in this case is considered different with respect to 0. I mean, we rejected the assumption that beta 0 was equal to 0, because in our specific case, beta 0, which is always the value of y, the estimated value of y when x is equal to 0. And in our specific case, x was the variable described in denoting the advertising expenses, and y the sales. So it is reasonable that even if the advertising expenses are 0, that the sales are positive, okay, are different from 0, okay? So in this, and so beta 0 represent the expected beta 0, okay, beta 0 is the expected level of sales for a store with 0 advertising expenses. Okay, so it's reasonable. The result we got is very reasonable, that even if a shop does not have advertising expenses, has at least a positive volume of sales. And so this essentially was what is established also by this test. Is it clear? Should I repeat or?
No, it's clear. Thank you.
Thank you. Welcome. So guys, again, turn on your microphone. Whenever you have a trouble, turn on your microphone. Stop me. I repeat. Okay, now I go to exercise B. On a sample of 70 males aged between 30 and 40 years, the annual income Y was detected in thousands of euros and years of education X. So you selected therefore a sample, so the dimension of the sample is 70, and you made already this computation. You have the sum of all the yi, therefore you have the sum of the annual income of the 70 male in your sample, you have the sum of the squares of the annual income of all these individuals, the sum of the years of education of each of the 70 individuals in their sample, the sum of the squares of the years of education of each individual in the sample, and you have the sum for each individual of the product between annual income and years of education. These are the information already provided. So you have the data, you computed it, okay? Okay, you computed them. Suppose, I mean, this helped me to give you exercises, otherwise I should have given you tons of data, then you have to spend all the time to do this computation, but I'm not interested so much in see if you are able to do a sum, okay? So this will allow us to see, really to do exercises helpful to learn. So you want to study the income of this individual as a linear function of the years of education. Okay, so study the income as a linear function of year of education. So in other terms, we assume that the expected level of income given the year of education is a linear function of the year of education. So we are assuming that the conditional expectation of y given x is a linear function of x. So first question, estimate the slope and the intercept of the linear regression model. Again, which is beta 1? Beta 1 is the slope, or coefficient of regression. To estimate it, we know that a great estimator is beta 1 hat. Beta 1 hat is the covariance over the variance of the regressor, or if you want, the codeviance over the deviance of the regressor. Remember the hat because I want to mean that these are computed on the sample, okay? And remember the codeviance, we have two alternative formulas of the codeviance, and depending on the data we have, we are forced to use a particular formula. Since we have the sum of the cross product, we know that the codeviance can be computed as the sum of the cross product minus the dimension of the sample times y bar times x bar. So we need to compute also y bar and x bar, the sample mean of the average income in the sample and the average income, the average year of education again in the sample. So, okay, guys. Okay, so guys, here you see the sum of the xi yi minus n x bar y bar, which is the deviance. Again, we have two formulas for the deviance, either as the sum of the xi minus x bar to the power 2, but we do not have this information, or as the sum of the xi of the square of the xi minus n times x bar square. So again, we have almost all the information. We simply have to compute x bar and y bar. So you see here I reported the formulas. So below, before doing the computation, I told you that we need to compute x bar and y bar, you see. So y bar is the sum of the yi divided by the dimension of the sample, which is 70. X bar is the sum of the xi, we have it, divided by 70. So these are the sample averages. So we can substitute here in the formula the sum that we have above, minus 70 times x bar, which is reported here, times y bar, which is reported here, and this numerator is the codevariance of xy. And we have the sum of the xi square, we have it above, minus n times x bar raised to the power 2, so minus 70 times x bar raised to the power 2. Do the computation, and what you get is this number. So this is 1.64, which is beta 0 hat, again, y bar minus beta 1 hat times x bar. So y bar is here, x bar is here, beta 1 hat is here, so insert the data in the formula, and you get 2.21. Again, to make practice, because in the exam I can even ask you to make an interpretation, and to be able to interpret the result of a regression model is fundamental. Otherwise, if you are able to do computation but you know nothing, doing computation is completely useless. You must get information and you must be able to interpret the information. So, which is the interpretation of this value? So remember, the variable y is the income, annual income of the individual in the sample of each of them, and the variable x, the year of education. So talking about our sample of 70 individuals, we can say that for every additional year of education, so if you increase the education of a person inside our sample, we have an average increment on the annual income of 1,640 euro, because remember that the unit of measure of y was thousands of euros. So this means the interpretation is the following. Concerning the 70 individual in our sample, for every increment of 1 year of education, so for every additional year of education, we expect on average an increment in the annual income of $1,640 or euros. Which is the interpretation of this beta 0 hat? Well, remember, concerning only the sample of our 70 male, we can say that the expected level of income for a completely uneducated individual, that is an individual with a scholarization equal to 0 year, is an annual income of $2,210. So this is the expected level of income for inside our sample, okay? Inside our sample, for the 70 people we have, the expected level of income for one individual in our sample having what? A level of education equal to 0 years, so 0 years of education. These are the interpretation. I'm talking about our sample because these are estimate number obtained by making the estimate considering specifically our 70 individuals. Okay, then beta 0 and beta 1 concern everything, the population, but are unknown. Okay, now, I repeat, stop me whenever you have troubles. Decompose the total deviance. We know that the total deviance is the total sum of squares plus equal to the residual sum of squares plus the explained sum of squares. To review, is the deviance of y equal the deviance of the residuals plus the deviance of the regression. If you remember, the deviance of the regression can be written either as beta 1 hat square deviance of x or beta hat 1 times codeviance of xy. Same result. So we want to decompose the total deviance. Can we split the total deviance? Which information do we have? Well, for sure, we can compute the deviance of y. Why? Because we have the information. Remember that the deviance of y is either the sum from I equal to 1 to 7 of what? Parentheses, yi minus y bar, close parenthesis, to the power 2, but we do not have this information. But can also be computed as the sum of the squares of the yi minus n times the average of the yi raised to the power 2. So we have the information to compute the deviance by using the formula. I reported here, you see, I reported the formula. This is reported among the data. N is 70, y bar has been computed here, which is 2567. Raise this 2567 to the power 2, do the computation, and this is the total sum of squares or deviance of y. Now we want to compute what? Can we compute the residual sum of squares or deviance of dispersion directly, deviance of the residuals directly? No, we can't, because in order to perform this task, we should know the sum from I equal to 1 to n of ei to the power 2, but we do not have this information. But who cares? Can we compute the explained sum of squares? That is, can we compute the deviance of the y hat, the deviance of regression? Well, here I reported the formula, for example. If you want to use this formula, you need beta 1 hat squared. Do we have it? Yes, we computed beta 1 at point A. Do we have the deviance of x? Well, we can compute it now. Or we computed it previously. We can compute it now. I saw that I wrote it here. That, oh, no, we computed already also. Yes, remember, we computed here already the deviance of x, which was this number. So we have everything. Beta 1 hat, so is this one. And the deviance is this one. So we need to do this to the power 2 times this one. And this gives us the deviance of regression or explain sum of squares of deviance of y hat. So we did the computation. Again, remember the decomposition of the deviance. You can find that the residual sum of squares as the total sum of squares minus the explained sum of squares. So the residual sum of squares, also called deviance of the residuals, is equal to the total sum of squares minus the explained sum of squares. That is, total sum of squares is the deviance of y. So the deviance of y has been computed here. Minus the explained sum of square, which is the deviance of regression, has been computed here. So do the operation and you got this now, and you get this number. So this is the decomposition. Now, okay, evaluate the goodness of the fit of the model. When? Well, we know that can be computed either as correlation, sample correlation between x and y raised to the power 2. Or alternatively, you can compute it as using the general formula. By definition, the R square, even with the multiple regression model, is explained sum of squares over total sum of square. I think I did only this way this time. Yes. Evaluate the model goodness of the fit, simply capital R square, so R square, ESS over TSS. So we computed them here, ESS, TSS, and I got 0.92. 0.92. If you want, you can compute also using the relation with the correlation coefficient. However, in this case, you have to compute first the correlation coefficient. Only to review, which is the correlation coefficient, guys? You can, the covariance divided the square root of the product of the variances. Or alternatively, the codeviance. You have the codeviance, which is this number. So if you want, you can write as the correlation. If you want, I write, no, since I have the number, I can add it. If you want, you can also write equal to correlation coefficient to the power 2, and to review is the codeviance. Which is the codeviance, guys? The codeviance is, oh no, perché mi sono messo a scrivere? This number, 1393. 13,93, 13 again, I think 13, no, 13,13. 1393,13, so sorry. Let me cancel. 93, here square, okay, comma 13 divided the square root of the deviances. The deviance of y is here, so 24, 93. 93, comma 31 times what? The deviance of x. The deviance of x, which is 850,29 times 850,29. And remember, this must be raised then to the power 2. So essentially, you can raise directly this to the power 2 divided the product of the deviances. And if you do the computation, you get the same number. If you have a small difference, it's only because you use the difference decimal, but the result should be perfectly the same. So both way, you can follow both way to get the R square. Again, exercise. What does this mean? What does the R square establish? This establishes that the 92% of the variability of y, so in our sample, so the 92% of the variability of the annual income for the 70 male in our sample is explained by its linear relationship with the number of years of education. So our model, so the goodness of the fit of our model is high because is the 92% of the maximum possible level of goodness of the fit, because theoretically the maximum value is 1. So 0.92 is the 92% of 1. So it's very huge. Okay. Which is the expected income of a male with 13 years of education. Guys, as I told you, one of the main purposes for which you study a linear regression model or you estimate a linear model is to make forecast. Suppose that inside your sample, you do not have an individual with 13 years of education, for example. Suppose you have with 14 years, with 10 years, okay, with 8, with a lot of, with 6, with 5, etc., etc. And you are interested in doing a forecast on the expected level of income for an individual with 30 years of scholarization. So what can you do? Well, you have your estimated straight line. Which is your estimated straight line? yi 2.1, which was the estimate beta 0 hat, plus beta 1 hat, which was this one, times xi. So you have simply to insert into xi 13, and here to put it in evidence, I wrote that y hat, the forecasted level of annual income for an individual with 13 years of education is simply obtained by substituting here into xi 13 and by doing the computation. So the expected level of annual income for an individual with 13 years of education is about 23,510 euros or dollars. Okay, but this is only an estimate, guys, an estimate, a forecast that we perform by using our estimated model. Test at a tail probability of 5% the significance of the coefficient of regression. Which is the coefficient of regression? Beta 0. No, beta 0 is the intercept. The coefficient of regression is the coefficient of the regressor, so is beta 1. So we want to perform an hypothesis testing concerning beta 1. And when you do it in the exam, you have to explain, guys, did I assume that the errors are normal? No. So we cannot follow the same procedure we followed previously. I mean, the procedure is the same, but something changed. However, we are in the case in which the dimension of the sample is 70. So look that you have to make this observation. N is 70, which is huge. Therefore, we know that the sample statistics is, no, sample statistics, yes, the statistic test is the same because you have beta 1 hat minus beta 1 0 divided the standard error of beta 1. But beta 1, 0, that is the value of beta 1 under the null assumption, is 0, because test if the coefficient is significant, it means that you have to test beta 0 equal to 0 under the null, beta 1 equal to 0 under the null against the alternative beta 1 different from 0. So beta 1, 0, the value for beta 1 under the null assumption is 0, so I substitute, and I get exactly the same statistic test I used previously, the same statistic test reported in the theory. But in this case, something changed, because, oh, here I forgot the 0, guys. I forgot the 0. So remember that in this case, we know only that the asymptotic distribution, thanks to the central limit theorem of the statistic test, so asymptotic distribution of the statistic test under the null assumption is a standard normal random distribution, a distribution of standard normal random variable. Okay, so formally everything is equal. The only exception is the distribution. The previous case was an exact distribution, which was a student's t with n-2 degrees of freedom, and this occurs when the errors are normal. Otherwise, if you don't, the errors are not normal, or you do not know the distribution of the errors, if n is huge, you have that the asymptotic distribution is a standard normal. So for other things, the computation are essentially the same, because now we need to do what? Previously, we computed the observed value t ops. Now we compute theta ops, okay? The observed value of this theta statistic test. So we need to insert into the formula, into beta 1 hat, the estimate we got previously, which was 1.64. Then standard error of beta 1 hat, I told you not to remember it, but is the square, I mean, if you like, you can remember, okay, s hat square over the deviance of x. But which is the meaning of s square hat? Is the deviance of the residuals. The deviance of the residuals is equal to the deviance of E divided n-2, or also RSS divided n-2, the residual sum of squares divided n-2. But we computed the residual sum of squares or deviance of the residuals previously. n-2, how many observations do we have, guys? 70. 70 minus 2 is 68. Deviance of x has been computed already in the first step, was 150 and something. So you see n-2, 68. This one, 850 and something. Beta 1 is here. And if you go back, the deviance of the residuals has been computed here. The deviance of the residual or residual sum of squares, which is 220.78. Oh, sorry. So we got this result. Guys, what I told you before, remember, I wrote here, remember that this is a system of hypotheses that we are going to test under the null beta 1 equal to 0, under the alternative beta 1 different from 0. Okay, we finished the exercise, then we will do the break. Okay, but let's finish this exercise and let me see. Cosa dobbiamo fare? We need to perform it at 5% significance level. So this means that we need to find two critical values on the table of the theta. So alpha, the significance level, is 5%. So alpha over 2 is 2.5%. Again, take the table in this case of the theta. You have to find the value of the theta such that this white area is 2.5%. That is, the green area is 97.5%. So again, we did it so many times with this number. Search here the first 0.975. Okay, you get it here exactly. So go here, you have 1.9. If you go above, you get 0.06. So the value here, so that the amount of probability on if right side is 2.5% is 1.96. So we have two critical values. This distribution is symmetric, so the two critical values are plus and minus 1.96. You see, I wrote the critical values here. So this is the observed value of the test. These are the critical values. Again, you have to compare the observed value of the test with the critical values of the test. The observed value of the test falls clearly outside the interval having as extreme minus 1.96 and plus 9.6. So this means that we reject the null assumption in favor of H1. So we believe that the year of education play a crucial role, an important role in explaining the level of the income. So in particular, that there is really a linear relationship between the expected level of income and the year of education. And here are all the explanation. Guys, if you want, yes, I think, because after the break, wait a minute, after the break, we will do the last exercise, this one. I will explain this output. Then I will show very quickly the last two exercises. No, the last two simulation I added, mock exam I added. Then I think that if you finish earlier, we can go away earlier. If you have, I don't know, don't say earlier because I talk everything every time. Then I start to talk, I never finish. But I will answer also your question. I mean, if you finish too earlier, I am available for your question. Okay. Okay. So guys, now you can rest. So I think that we can start again at 20 minutes to 4 p.m. Okay, at 20 minutes to 4 p.m. So in other terms, at 40 minutes past 3. Okay, past 3 p.m. So you have 16 minutes. Go, guys, to rest unless you have something to ask. Otherwise, no problem. Okay, we are only 16, guys, or 15. Not good, but okay, guys, you can go to rest unless you have something to ask. Obviously, you can ask me. Otherwise, go to rest a little bit.
Professor?
Yes?
Yes. May I ask you something very quickly?
Yes, you can. Yes,
it's
obviously.
About the meaning of degrees of freedom. Because I read they should be like the number of the variables that can move freely. Is that right?
Yes. No, the number of observations that are free. Yes, because when you estimate, for example, I told you when you estimate, for example, as I told you this morning, for example, when you estimate let me share, when you estimate the sigma square, for example, of a regression by using s square, what happens that you lose 2 degrees of freedom in the sense that in order to estimate s square, you need to compute before beta 0 and beta 1. You have to estimate them. So in this sense, you less sort of 2 degrees of freedom because 2 informations, I mean, in the sense that you lose 2 information because 2 information are necessary to estimate the parameters beta 0 and beta 1. So you don't use the true beta 0 and the true beta 1, but estimate. So 2 of your information, so it's like losing 2 informations. Okay, so
I understood. Thank you, Professor.
I
understood. Thank you.
Okay, welcome. Okay, if you have no question, okay. But tomorrow I mean you have 3 full hours, so prepare your question, everything. Okay, guys, we continue. We continue. So we take again the previous exercise. No, dove siamo? Okay, we finish the exercise, sorry. Exercise C. So, suppose you have the data with annual frequencies for the consumption Y and the disposable income X in a given country for a period of 10 years. So you have data about the consumption and the income of a given...
Professor?
Yeah, oh, see,
Yes.
thank you. I have to share. Yes,
Yeah,
thank you. Thank you, thank you, thank you, thank you. So, do you see now? Yes, now stop me if you don't see, okay? Suppose you have the data with annual frequency for the consumption Y and the disposable income in a given country for a period of 10 years. In particular, so your sample, guys, is a sample made up only by 10 observations. Okay, 10 observations, one concerning the income and the other the consumption for this particular country. So this is a very small sample. In particular, given your sample, suppose you have the data, you made the computation and you got this deviance, this estimate of the deviance of Y of the consumption, this estimate of the deviance of the disposal income, this estimate of the codeviance, so this and the sample mean, small x bar, 8, and small y bar, so the average consumption in the 10 year and the average disposal income in this 10 year. So the first question is estimate the regression line. To estimate the regression line, obviously you need to compute beta 1 hat and beta 0 hat. Beta 0 hat is the estimator of beta 0, beta 1 hat is the estimator of beta 1. After having computed their values in the sample, you get estimates. So beta 1 hat is the codeviance divided the deviance of the regressor. The regressor is the disposal income. Okay, so insert the data. Code codeviance is the same, guys. Code of codeviance is the same, okay? Code of codeviance is my notation. So the codeviance is 21, the deviance is 28. Make the computation and you get 0.75. Okay, beta 0 hat again is the sample mean of the dependent variable Y minus beta 1 hat times the sample mean of the regressor X. So we have all the information because X is here. Oh, guys, please. Yes, here is 8, but I think I did the computation rightly because I explained the same lecture a couple of days ago in Forli, and yes, I checked at the time, so this is 8. Okay, so I wrote 6, but it's 8. Okay, so 8, and but the computation are right. Okay, so 9.6 minus beta 1 hat times 8, and you get this number. Again, to play, guys, provide an interpretation of this data. So beta 1 hat is the estimate. So this is the estimate in our sample. This is the estimate in our sample made up by 10 observation of the slope of the unknown regression line. Okay, so, okay, of the true line, which is unknown. Okay, this is our estimate. And in particular, which is the meaning? Look at the variable. If increase the income of 1 unit, the disposal income of this country of 1 unit, you expect an increment of the consumption of 75 cents. So, but this does not mean that for sure we have such an increment. Okay, so if you increase the income of 1,000 euros, you expect an increment of the consumption. I'm using, obviously, guys, a small number because here we talk of billions. You get you expect an average increment of 750 euros. I'm talking, okay, here we're talking about consumption and disposal income of a country. So we are talking of billions of euros. So, okay, but the interpretation is the following. If you reduce the disposal income of €1, you expect a reduction of the consumption of 75 cents, okay, for this country in this particular period, of 10 years. Which is beta 0 hat? Is this one. Which is the meaning of beta 0 hat in this case? Beta 0 hat is the estimate of the intercept. So is the intercept of our estimated straight line. So is the average or expected level of consumption in the period considered. In the case, the disposal income is equal to 0. So it's 3.6. I don't know here which was the unit of measure for billion. I don't know. Million. I don't know. However, this is the expected level of consumption of this country in case of disposal income equal to x equal to 0. But this is expected according to the estimated straight line, okay? It's not the true beta 0, okay? But always, the interpretation you see are always similar, okay? Because the meaning of beta 0 is the estimate of the intercept. Beta 1 hat is the estimate of the slope, which is the meaning of the slope of a straight line, which is the meaning of Q, the intercept of the straight line. So compute the linear correlation and the R square. Well, the linear correlation coefficient can be computed as the covariance over the square root of the product of the variances, or alternatively as the codeviance divided the square root of the product of the deviances. Here, if you look above, we have already all these data because you have codeviance, you have the deviances. So put inside and we got 0.72. So we see that in this case, the R square is smaller compared to the previous exercises we did together. However, there is still a positive degree of linear relationship for the disposal income and the consumption inside our sample. So you see that this positive relationship. However, for the correlation tells nothing about the direction of the dependence because correlation of xy is equal to correlation of yx. And another thing you can say is that the degree of linear dependence inside your sample is the 72% of the maximum positive degree of linear dependence, because the maximum is 1 of positive linear dependence, and 0.72 is a 72% of 1. How can you compute the R square? Well, in this case, since we computed already the correlation coefficient, and I told you that in the simple linear regression model, there is a very easy formula to implement to get the R square, which is simply R square equal to the correlation coefficient raised to the power 2. If you raise it to the power 2, you see the goodness of the fit is this number, 0.5, well, essentially 0.52. So you see, it's not really huge. What we can say is that the 52%, about the 52% of the variability of the consumption in our sample is explained by the estimated straight line. That is, it's explained by its linear relationship with the x is the disposal income. So only about the 52% of the variability of y of the consumption in our sample of 10 data is explained by the disposal income. So it's not huge. So there is, we can say, well, the goodness, we have an average, I mean, a discrete maybe, or is too hard, sufficient, well, I don't know. The best things you can do is to say that the 52% of the variability of y is explained by our linear model. For me, it's an average level of goodness of the fit. What can you say? What can we say? Okay, so it's not really good. It's not really bad. I mean, it has a contribution. but it's not really strong contribution, an average contribution, acts as an average degree of contribution in explaining the behavior of Y. Okay, then I asked you, let me see. Obviously, guys, when you study, you have to ask yourself, I was able to compute the R square in a different, using a different formula. Remember that the R square, guys, no, I do not do it. The R square is also, this is the general formula that works always, the one I'm writing. This is true only in the simple linear regression model. But what I'm writing now is true also for the next part of the course. Well, I mean, with the professor of econometrics, divided the total sum of squares. But remember, do we have ESS? ESS is, you can use several the information you want. You can write, let me write it in several ways. ESS, remember, ESS is given by beta 1 square. Which is beta 1 square? This one, 0.75, 0.75 times the deviance of x. Deviance of x is 28, divided the deviance of y, which is the total sum of squares. Deviance of y is 30,4. So if you do the computation, you should get the same result. Alternatively, as I told you before, explain total sum of square is the same, which is 30,4. Alternatively, I told you that you can compute the explain sum of squares. Sorry, I forget to report the square. Here, guys, I told you beta 1 square times the deviance of x divided the deviance of y. This is the formula we used also in the two previous exercises. But as I told you with voice, without doing the exercise, you can, without doing the computation, you can compute it also as beta 1 hat, which is 0.75 times the codeviance between x and y, times the codeviance between x and y is 21. So if you do this computation, you should get the same result. These, and these must provide the same result, okay? Same result for the R square. But you have this formula, okay? This formula, our formula I explained this morning, and I outlined them in blue when I explained to tell you that they were important. Then I asked you, estimate the standard errors of the estimator. If you have such a question or something similar, I will provide you this formula because I do not ask you to remember, as I told you several times. However, here I reported the formula, the square root of s hat square times 1 over n plus x bar deviance of x. So we have x bar, and we can raise it to the power 2 because it was 8. Then we have the deviance of x, which is 28. We have 1 over n because we have an observation, so we have 1 over 10 plus 8 to the power 2, the deviance of x, which was 28. We do not have s square. We do not have s square, so we need to compute it. So for the moment, wait, because we are going to compute it. SE beta 1, the standard error of beta 1 is, I forgot the hat, s hat square over the deviance of x, everything under the square root. Again, deviance of x is here. What we need to get s square. To get s square, if you remember, s square is the residual sum of squares, is the deviance of the regressor. So s square, I repeat, s square is the variance of the residual. The variance of the residual is the deviance of the residual divided n minus 2. But the deviance of the residual is also called residual sum of squares. Do we have the information residual sum of square equal to sum of the squares of the EI to the power 2? No. However, we have other information that allows us to get the residual sum of squares. Remember that the residual sum of square, thanks to the decomposition of the deviance, can be computed by doing the total sum of squares minus the explained sum of squares. But the total sum of square is the deviance of y. We have it. The explained sum of square, okay, is the formula computed above, is this one. You see, when I told you 0.75 square times 28. This is the explained sum of square. Okay, reported here. So put the number here, divided by 8, you get 1.83. So substitute 1.83. Okay, guys, here I computed also S hat, which is the square root of this one. In the regression, guys, I still have to tell it. This is called standard error of the regression. If you want, call it standard error of the regression, which is essentially the estimate of sigma is called standard error of the regression. Standard error of the regression. Okay? Standard error of the regression. Okay? Okay, guys? Okay, assume that the errors, okay? Assume that the errors are normal. Build a confidence interval at a 95% confidence level for both parameters. Guys, an observation. We are required to build confidence interval for both parameters. So that is for beta 0 and beta 1. Okay, don't write confidence interval for beta hat 0. No, it's for beta 0. Don't write confidence interval for beta 1 hat. No, for beta 1 is the confidence interval. You build confidence interval and you test hypotheses concerning the unknown parameter of the model, beta 0 and beta 1. Guys, this assumption is fundamental. Why? Because suppose that here we do not assume that the errors are normal. Are you able to build a confidence interval at a 95 confidence level for both parameters? You can't. Why? Because n in our case is only 10. 10 is really very small sample. So in this case, this is really a crucial assumption, because thanks to the fact that the errors are normal, we are exactly in case A, that is the reference distribution, both in building confidence interval and in performing hypothesis testing, is the student's T with n-2 degrees of freedom, in particular with 8 degrees of freedom in our example. So build a confidence interval. So remember, the formula are beta 0 at plus minus the value you find on the table of the student's T with 8 degrees of freedom, because we have 10 observation minus 2, so 8 degrees of freedom. Okay. And since the confidence level is 95%, this means that alpha is 5%. Alpha over 2 is 2.5%. So we need to find on the table of the student's T the value that has an amount of probability on its right side equal to 2.5% of a student's T with 8 degrees of freedom, I forgot to say. So we have beta 0 hat, we computed it in the previous step, first step, put it here. SE beta, has the standard error of beta, has been computed here, of beta 0, and this is of beta 1. So if you want, guys, to be faster, you see the formula are the same, okay? But here you have beta 1 hat and its standard error. Now we need to take the table again to look for the two critical values. I mean, the two, in reality is one, because not critical values, two values. The table of the student's T, we want that this, no, this is square. We want that this area is 2.5%. So here, 8 degrees of freedom, so go below. The number is 2.306. Yes, 2.3, you see the arrow, 06, 2.306. Substitute here, again. First compute the operations with the minus. So guys, remember, even if you hate mathematics, first of all, do the product. This times this, then do this number minus the result of the product. Don't do 3,6 minus this one and then multiply the result by 2.09, obviously from elementary school, but pay attention, okay? The order of the, remember, the order of the operation, okay? But what I wanted to say, you have two cases, the one in which you have minus here and the one in which you have plus here. And the first one I want you to compute is the case with minus, so you report it here, the lower extreme, and here the upper extreme, here the lower extreme, and here the upper extreme. You see, look at this confidence interval. You see how this is really huge. And in particular, you see, you have that the lower extreme is even negative, and is really huge. Guys, why? Yes, because guys, in this case, we have tons of variability, a huge variability. Why? Because we have really a sample which is really small. Only with a sample of 10 observation is really small. And so the standard errors are huge. Standard error are huge, okay? Because n is small. So this standard error, in particular this one, is very huge because n is small. With higher n, the standard error is smaller. So someone is writing something? No? Maybe someone wants to get inside the room now? Yes, now. So guys, okay, so we built these confidence intervals. Let me see if you have another question. No, stop here. So guys, now we finish with the exercise, but I want to show something, and I decided maybe I can even give this exercise on the exam. Maybe, I don't know. For sure, you had something about the linear regression model. This is for sure. In particular, guys, this is was the text, not the complete test of the exercise given in an exam of econometrics at the master degree in Forlì, in another course. I do not remember the course, and there were questions, but we will not see the question. I didn't copy the question, but I reported only the data of the exercise because I wanted to explain, because I remember the student at the time told me that we were unable to read this one, and explained how to read the table. And so, even if, guys, and now I explain what you have. Guys, we read together, so consider the following multiple regression model. We studied, guys, the simple linear regression model. You have to study the multiple regression model in applied econometrics in the real course. However, I want you to anticipate something without doing proof, but only something that you can compute even by using intuition with all the things you studied with me, so you can understand maybe why the simple linear regression model is so fundamental, also to understand very well the multiple regression model. So everything mathematical will be explained by other professor. He will do his own exercises, but I did it in this way. I read, consider the following multiple regression model that measures the connection between wages and education measured in years together with some other factor. In particular, we have the following variable: wage, measure hourly wages expressed in dollars. Female, a dummy variable, as you will see probably in econometrics, is a variable that can assume only two values. If the first individual in your sample is a male, the dummy variable assumes the value 1. If the first element of your sample is a male, it assumes value 0. If it is a female, value 1. Then look at the second individual. If the second individual in your sample is still a male, it assumes 0 and value 1. So these are, if you have 100 observation, 100 individuals, for each, then you have, the observation will be 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, depending on the gender of the individual you consider. So for each of these individuals, you detect the wage, you detect the gender is captured by this random by this dummy variable, the education, the years of schooling, and the experience in the labor, okay, when you work, experience in work. And the model that was estimated was the following. Guys, remember, y, instead of writing yi or simply y equal to beta 0 plus beta 1 times x, here we have plus epsilon. Here we have a multiple regression model in which the variable y is the logarithm of the wage, but we do not care that it's logarithm of the wage. Simply is the wage, this is our y. This plays the rule of y, the yi, capital Y1, capital Y2, capital Y3, etc., etc. Alpha here is the intercept, so plays the rule of our beta 0. Delta 0 is instead the coefficient of regression associated to the variable called female. So female can be seen as the variable, I don't know, capital X1 was coefficient instead of being called beta 1 is called delta 0. So this is a constant, a parameter of the model. This is another parameter. This is the first regressor, which captures the gender of the individual. Beta 1 is another parameter which is associated to the variable education. So this can be seen capital X2 and beta 1 is its coefficient. Delta 1 is the coefficient associated to another variable which has been obtained in this way as the product between the variable female and education. I explain what does this mean. Suppose that the first individual of your sample is a female. And what you have here, the first observation here is 1, because the first element of your sample was a female, times what? The education of this girl. Suppose that the second individual in your sample is a male. In the case you have, for the male, you have 0 times its education, which gives you 0. So this essentially, this variable assumes value exactly equal to the education whenever you have a female, and assume instead value 0 whenever you have a male. Okay, remember, it's like having 100 individuals, and for each individual you detect gender, education, this variable, the value of this variable, I repeat, only for female is equal to education, only for male is equal to 0. And then you have beta 2 is another coefficient of regression times experience, which is this variable. And furthermore, you have another regressor, which is, we can call it x1, 2, 3, 4, 5, x5, which is the variable experience raised to the power 2. That is, all the values of experience of each individual are raised to the power 2. So if you, obviously, you cannot do it with your hand. Suppose you have a number of observation, a given sample, put into your data set, this was performed with the software called Stata, put the vector, your observation concerning, for each individual concerning the logarithm of the wage, the gender, the education, the product between female, the gender and the education, the value of the experience and the value of the experience square, order to the software, provide the OLS, ordinary square estimation of this model. And then the software produces an output. And now what I want you to do is to review again with you what we studied in the simple linear regression model and the extension I did, the only few extensions I did for the multiple regression model to show how to get the meaning of this number and how can you get this number. So first of all, I color the things that are really necessary. Here is really necessary to know the number of observation. No, so let me cancel. The data which are really fundamental, because some data are not necessary and I want you to compute them. I mean, I'll explain how to compute them. Then maybe these two, I select these two, for example. Let me see, then I will explain everything, okay? Okay, these are the only data relevant. Even without the PC knowing this data, you are able to compute everything else with what you studied with me today. And in particular, I start from this third table, from this table. Then we will analyze this one and finally this one. Start from the last one. I explain the meaning of this table. This is an output which is done automatically. If you ask to Stata or to a lot of software, estimate this model, the computer makes the computation for you, and this is the typical output. Okay, typical output. And look here, what is, I explained this out because it's very important also for the next part of the course, and I prepared also exercise in the last two simulation I added today. So look with me, coefficient, here you see female educ, FEDUC, which is this one, FEDUC. Well, what is this number, for example? Minus 0.3294. This is the estimate of delta 0. So is what we called sigma at 0. Okay, sigma at 0. EDUC 0.0844. Are you able to see this number, guys? 0.0843801 is the estimate of beta 1. So this is beta 1 hat. And now FEDUC, this is the estimate of delta 1. So is delta 1 hat. Expert is the estimate of beta 2. So is beta 2 hat. Square, this means square of experience, is beta 3 hat. That is the estimate of beta 3. Cons is is the constant, what we call beta 0 in our simple in a regression model, and here is called alpha. In particular is beta 0 hat, or if you want, alpha hat. So these are the estimate. Remember, we estimated the regression line, we estimated always beta 0 and beta 1 by computing beta 0 hat, beta 1 hat. We have the formula. Here, okay, we don't have the formula are different, okay? You don't have to learn this formula. This is a topic that is not related to me, but I want you to realize that these are the estimate. Remember that I have shown you which is the standard error of beta 0 hat. I told you that you do not have to remember the standard error, but for beta 0 hat only to talk is the square root of what? S hat square times parentheses 1 over n plus x bar square over the deviance of x. Okay, remember, we computed it. I told you, don't remember, but this is the standard error. The standard error of beta 1 hat is the square root of s hat square over the deviance of x. I'm simply talking, guys, and I told you, don't remember this formula, but we computed it in the previous exercises. Okay, well, in this column, guys, for each estimate, you have the corresponding standard errors. But this, okay, is done by the software. Okay, this and now, without having the software, but having only this information, you are already able to compute these values. And I tell you which is the meaning of this value. And this is something that is done automatically, but by almost all statistical and econometric software. Maybe the table is written in a little bit different, but all software make this computation in automatically. What do you have here? You see this column T. This is, pay attention, is the observed value of the statistic test. In particular, 1, 2, 3, 4, 5, 6. These are the observed value of 6 statistics tests. In particular, this one is the observed value, pay attention, associated of the statistic test used to test if the coefficient of female, which is delta 0, can be considered significantly different from 0. That is the statistic test associated to the hypothesis delta 0 equal to 0 against the alternative delta 0 different from 0. The one below, for example, this 9.64 is the statistic test associated to the test in hypothesis in which under the null you have beta 1 equal to 0, under the alternative you have beta 1 different from 0. So essentially these are the statistic tests to test if one by one, if all these coefficients but one by one are significantly different from 0 or not. Essentially are the statistic test we computed before when we tested if beta 0 was significantly different from 0 and beta 1 was significantly different from 0. As you remember previously, guys, how can you compute this statistic test? Remember, we had beta at 0 minus the value under the null. Which was the value under the null? 0. Beta at 0 over is standard error. So here, since the alternative under the null, you have the assumption that the parameter is equal to 0. In all these cases, how can you get this? Very easy. It's simply the ratio between, for example, sigma 0 hat divided the standard error of sigma 0 hat. So to get this column, the observed value of the statistic test, of these 6 statistic tests, you have simply to do this divided by this one, this divided by this one, this divided by this one. So these are the observed value of the statistic test. As I told you several times, typically in statistics, you report, well, you can report if you perform a test using a given significance level, okay, you can report the critical value. But typically the statistical software or econometric software, when they perform this automatic test, they prefer to report the p-value because it's more informative. So in this column, guys, in this column, you have the p-values. Remember that the alternative is bidirectional. Okay, so to compute the p-value, you know what you have to do. For example, an observation. How many observations do we have? Look here, 526. So we do not need to assume that epsilon 1, epsilon 2, etc., the errors are normal. In this case, we know that the reference distribution is the standard normal. We did it before, guys. This corresponds to our case B. How can you compute the p-value in this case? The p-value is the probability that a standard normal random variable will assume a value smaller than this one multiplied by 2. The probability that a standard normal random variable will assume a value bigger than this one multiplied by 2. The probability that a standard normal random variable will assume a value smaller than this one multiplied by 2. When it is positive, remember, probability that a standard normal random variable will assume a value greater than this one multiplied by 2. The probability that a standard normal random variable will assume a value smaller than this one multiplied by 2, etc. So these are the p-values that you can compute if you want with the table you have. You can compute them, okay? So you see why they are informative, because remember that the p-value is the observed tail probability level. Now, what can you see immediately? Are you able to find some coefficient parameter that are really significantly different from 0? Well, the parameter associated to education, beta 1, the parameter associated to experience, beta 2, look at the 0, 0. And the parameter associated to experience to the power 2, look, they have a p-value of 0.0000. So there is a super strong and incredibly huge empirical evidence supporting the fact that in determining the logarithm of the wage, the education, the experience, and the square of the experience plays a crucial role because they are highly significant. Now, what about this coefficient? Well, the constant, yes, is significant because you see, even if you consider a significance level at 1%, this is a p-value is much smaller. Okay, so this is also significant. Then you have 2 parameters. Well, female is not so significant because if you want to perform an hypothesis testing at a alpha equal to 1% or even alpha equal to 5%, observe that a 5% confidence significance level, this coefficient is bigger. So you accept the null, that is that this parameter is not significant. So at usual significance level, even if it's close to 5%, so the rejection is not, the acceptance is not strong, in this case, you can accept H0, that is the coefficient associated to female is not relevant. So according to this study, the gender does not explain the difference in what? In the wage. It seems that the gender, the fact of being a man or a female or a male does not affect it, even if, however, the rejection is not really strong, because you see, if you see that if you want to perform a test at a 5% significant level, you see you are close. So it's not really, you accept, then you do not reject the null, but there is some empirical evidence, okay, in favor of H0, that is that this parameter is not significant, but the empirical evidence is not stronger than in the other case. FEDUC instead is for sure completely useless. The interaction, this means that it seems that the fact that the individual, I mean, having a male that studied a lot or a female that studied a lot seems not to be really irrelevant. On the contrary, the sex, the gender itself can have some impact, maybe some, but maybe not. But FEDUC has no impact, so the education is really relevant itself. It's no difference if you have a very educated man or very educated female, at least in this data. Okay. So you see that you are able to compute this by yourself, coefficient, estimate, divided standard error of the estimate, and you get this number. You can compute this, as I explained, by using the table of the p-value, the table of the theta, and by making use of this number. So you see, what is this? 95 confidence interval. So here you see this number, This is a confidence interval at a confidence level of 95% for the coefficient of female, which is delta 0. We computed for beta 0 in our exercises, and for beta 1, here you have 1, 2, 3, 4, 5, 6. We had only 2 parameters. Here you have 6 parameters, so you have 6 confidence interval, 1 for each parameter. Are you able to compute them? You should have to say me, yes, for sure we are able. Why? Guys, how can you, this is the lower extreme. How can you compute it? Do you have the data? Yes, guys. Remember, which were the confidence interval in our cases? Beta hat, independently by beta 0 and beta 1, plus minus Q, T alpha over 2 with n minus 2 degrees of freedom, or plus zeta alpha over 2, times what? The standard error. Now, look in our case, the dimension of the sample is very huge. So as I told you, we know that the reference distribution is the standard normal. So this number is very easy to compute. It's simply delta 0 hat plus what? Zeta of who, guys? 1 minus alpha is 95%. Alpha is 5%. Alpha over 2 is 2.5%. So zeta of 2.5%. Zeta of 2.5%, we saw today already several times, is 1.96. So what you have, I repeat, you have the computation to get this number are the following. Sigma 0, which is this number, hat, plus, nothing minus because we compute the lower extreme first, minus 1.96 times what? The standard error. If you do this computation, you get exactly this number. This is instead the upper extreme of the confidence interval. So sigma hat 0 plus the theta alpha over 2, which is 1.96, times what? The standard error. So these are the extreme of the confidence interval. Last one, for example, which is consider a duc. Its coefficient is called beta 1. So here is a confidence interval for beta 1, and this value has been obtained by doing beta 1 hat plus, again, minus 1.96 times what? The standard error. The upper extreme, beta 1 hat, which is this number, plus 1.96 times the standard error, etc., etc. You see that everything is clearly linked very, very easily to what we studied in this lecture about beta 0 hat and beta 1 hat, beta 0 and beta 1, but also to what we studied previously about the computation of the p-value. Here is, you see, so every statistic test here, every observed value of the statistic test associated to the null hypothesis of non-significance of the coefficient is simply the estimate divided the standard error. So track. And the software does it automatically when you ask to estimate a regression model. Okay, so you see that only with these two columns and with this information, you are able to compute this column, this column, this column, this column. And these exercises are useful because you learn how to interpret the result of a regression. Otherwise, if you never think, when you see the first time you see an output of a software, you say, I understand nothing. In fact, instead, reason and try to verify why with yourself to repeat it. Don't take one example, take one row and then compute everything by following what I told you. We finish with this part, but now we go to this one. Essentially, guys, what is it? This is, guys, the decomposition of the deviance. And essentially, you need only these two data, or at least, guys, look at this column. You need only two of these three data. You can even have only the first and the last, the second and the last. I decided to select, for example, these two. Suppose you have only these two data. Now explain the meaning of these two data. These are concepts that you have also in the multiple regression model. You see, here you read with me. Source, model, residual, total, which is SS, guys. Sum of squares. Model sum of squares. The model sum of squares, guys, are the regression, are what we call explained sum of squares. So model sum of squares are the explained sum of squares. So the explained sum of square, obviously, to compute the explained sum of square here, you don't have to use the formula we saw today. Why? Because the formula we saw today was a formula in which you had only one regressor. Here you have several regressors, so the formula is different. However, the meaning is the same, is the amount of the total variability of y explained by this estimated model. Look, here you have residual SS. So these are the residual sum of square, 89 point, etc., are the residual sum of squares, or what we call deviance of the residuals. The one above, I repeat, are the deviance of regression, or explained sum of square is SS, okay? Or the deviance of the y hat, the deviance of the logarithm with the hat of the wage, okay? And total is TSS, total sum of squares. So the total sum of square is this number, is total sum of square, which is the deviance of y. Y is this variable, the logarithm of the wage. Is it necessary to have this data? No, it's not necessary, because if you do this, remember, total sum of square is residual sum of square plus explained sum of square. If you do this plus this, you get this one. Now, this means degrees of freedom. Guys, remember this morning, if you remember this morning, I told you without explanation, I told you, well, it's possible to show that the explained sum of squares divided by sigma square follows a chi-square with 1 degree of freedom, either exactly or asymptotically, as in this case. And I told you this morning, ESS divided by sigma square follows a chi-square with 1 degree of freedom because you have only one regressor. And I told you, in the model with the next professor, if you have k regressor, this will follow a chi-square. ESS divided sigma square will follow a chi-square with k degrees of freedom. Now, look with me, how many regressor do we have here? Female, 1, 2, regressor, not parameter, regressor, 1, female, educ, 2, female times educ, 3, experience, 4, experience to the power 2, 5. So the k I used this morning to denote the number of regressor, which was equal to 1 in our model, here is 5. So df, degrees of freedom, is 5. Then remember residuals. Remember that this morning I shown you that, and we use it, that S at square, which is the variance of the residual, can be used to estimate sigma square. And to get an unbiased estimator, the variance of the residual is the deviant, the residual sum of squares, which is this number, or deviance of the residual divided by what? N minus 2. Why 2? Because we have one parameter plus another parameter because we have one regressor. If you remember, okay, 1 n minus 2. And I told you, when you will work, and I wrote it, when you will work with the multiple regression model with k regressor, you will have n, you have to divide to get the variance, an estimator of the variance of the residual, you have to do the deviance of the residual or residual sum of squares divided n minus parentheses k plus 1, where k is the number of regressor. How many regressors do we have? 5 regressors, so 5 parameters. plus a constant. So n minus k plus 1 is n minus 5 plus 1 is n minus 6. Since we have 526 observation, do 526 minus 6, you get 520. Okay? Now, what is it, guys? What is it? This is the deviance of y. When you want to compute the variance of a variable, guys, to get, suppose you want to use an unbiased estimator, which is the variance of y when you want this, the unbiased sample variance of y, is the deviance of y divided n minus 1, because to compute the total, the variance of y, the unbiased variance of y, you lose a degree of freedom because you have to compute x bar to estimate mu. Remember what we used before doing this, we used s hat square to estimate the variance of y. Remember? And we divided the sum of the difference, the sum of the yi minus y bar to the power 2 divided n minus 1. Here is the same. You have 526 observation, n minus 1 is 525. Now, here instead, this I repeat is the sum, explain sum of square, residual sum of squares, total sum of squares, or alternatively, deviance of regression, deviance of the residuals, total deviance. If you divide, here guys, is called mean of the squares. In particular, this means mean of the squares, but you can call them, look at this one first. This one has been obtained by dividing the total sum of squares, that is the deviance of y, by n minus 1. But what is it, guys? This is an estimate of the sample variance of y independently by your regression model. This is what we studied already several lectures ago. This is what we called several lectures ago as s hat square. Okay, today for s hat square, we estimate the sigma square, which has another meaning. However, this is the deviance of y divided by n minus 1, an estimate that we do a lot of time. So this divided by this one gives this one. What is this number? This instead we encountered it this morning, is the residual sum of squares divided n minus k plus 1 gives you what? The estimate of sigma square. So this is what we called s hat square today, which is an unbiased estimate of sigma square, where sigma square, guys, sigma square is the variance of the error. So this is the unbiased variance of the residuals, because it's the residual sum of squares, or deviance of the residual, divided n minus k minus 1, n minus 5 minus 1. So this is what you use to estimate sigma square, where remember, sigma square is the variance of epsilon 1, epsilon 2, epsilon 3. We estimated previously, guys, also in our exercise. I'm repeating everything we did in our previous exercise, but previously we had only two. We have a regressor and a constant. Here, the concepts are exactly the same, however. What is it? This is simply, guys, this, the explained sum of square divided by k, which can be called, guys, variance of regression. Okay, this is the variance of regression. Okay, variance of regression, which is the deviance of the regression, or explained sum of square, divided the number of regressor. So you see, if you study simply by this knowledge, now you can compute everything. You see, we computed everything. But this, I repeat, is very useful because you learn, you are able to understand the link between the formulas that you will study and the numbers. Now, number of observation, I told you that was important. Remember that this morning, at the end of the lecture, I told you, if you want to test that our model is significant, you have to test if beta 1 is equal or different from 0. But then I told you, guys, I explained you another test, which is the F test. Okay, I told you this is not really important in our case, but I told you I explain it because then later I want to show this test when you have a multiple regression model. So to review with you, because I know that you don't remember, what I'm saying is that yes, we derive this result, and I told you in a model with k regressor, you have this statistic test to use. The explained sum of square divided by k, divided the residual sum of square divided n minus k plus 1, follows an f of Fisher with k and n minus k minus 1 degrees of freedom. So, and this statistic test is the one you need to use when you want to test if your regression is significant. That is, if beta 1, beta 2, beta k is equal to 0. Keep this in mind, and now I go back to the table, to this table. Dove siamo? Oh, che palle, dai. Dov'è? Okay. Now, how many parameters do we have? Remember, how can you test if this regression is significant? You have to test that jointly. Not here we tested the parameter one by one. Here you have to test jointly that sigma 0 equal to beta 1 equal to sigma 1 equal to beta 2 equal to beta 3 equal to 0. Under the null, you have that all the parameters associated to the regressor are jointly null. Under the alternative, that at least one of them is null. I told you this morning and a minute ago that what you have to do in this case, when you have multiple regression model, to test this hypothesis, you have to use the F test. And the test we just read was this one, was the explained sum of square divided by k. So what is it? How can you get this 69.22? This number divided by 5, which is already computed here, is the variance of regression. So you have equal to 11,854298 divided by what? The residual sum of squares divided n minus k minus 1. So this number divided by this one, which is this one. So essentially, this 69.22 is the ratio, is the observed value of our statistic test, which is the ratio between this number and this one. Which is the reference distribution? I told you, is an f of Fisher with k and n minus k minus 1 degrees of freedom, but k is 5. Okay? And the number of degrees of freedom here are n minus k minus 1, so 520. So this is the critical value of the, the observed value of the statistic test. Now, I told you that you reject the null, that is, you reject the assumption that all the coefficients are jointly equal to 0. That is, you reject the assumption that your model is not significant. If the value of the statistic test becomes bigger and bigger. Because if you remember, in the numerator you have the explained sum of square, which is good, and in the denominator, the residual sum of square. So bigger the value of the statistic test, more likely is that H0 must be rejected in favor of H1, that is at least one parameter of the regression is different from 0. And in particular, here is reported the p-value. Here, the probability that an f of Fisher, so the alternative in this case, guys, is on the right, okay, only on the right, because if this is close to 0, you accept H0. If this is far from 0, you reject H0 in favor of H1. So you have to compare the p-value. Here is reported the p-value. The p-value is the probability that an f of Fisher with 5 and 520 degrees of freedom will assume a value bigger than this one is essentially 0.0000. So what can we say? We can say that our regression is significant. So we reject H0 in favor of H1. We do not discuss the adjusted R-square because it's something that will be explained by the next professor. However, which is the R-square, guys? I told you, the R-square is the explained sum of squares divided the residual sum of squares. So the explained sum of square is this number. The residual sum of square is this number. So do the ratio between, cosa ho detto? Forse non ero concentrato, ho detto una cagata. The residual sum of squares is the ratio between, guys, residual sum of, mamma mia, explained sum of squares for this number and total sum of square. So 59.27, etc., etc., divided 148.32, etc., etc. So this, if you do this relationship, the ratio between the first number here and this number, you get the R square. I told you that in this case, you don't have a correlation coefficient between x and y, because you see you have one y, but you have 1, 2, 5 different x, okay, x1, so okay. And avoid adjusted R square, you will see it in the future. So you see that the goodness of if it is about 40%, is not really huge, but there is some explanation, but not so huge. Root mean square error. Root mean square error. The root mean square error, guys. Remember, guys, how many parameters do we have? Alpha, delta, 0, beta 1. So we have 6 parameters here. 5 are the parameter associated to the regressors. 1 is the constant. However, there is also another parameter, as I told you this morning, which is sigma square. The estimate of sigma square is S hat square, which is reported here, okay, which is the residual sum of squares divided n minus k minus 1. So this is the estimate. This is S hat square estimated. This is unknown, is a parameter, because it's the variance of the error, is the variance of epsilon 1, variance of epsilon 2, etc., variance of epsilon 526. All these variances are equal, assumption. And this root mean square error is the estimate of sigma. So the estimate of sigma will be simply the square root of this number. So if you take the square root of this number, you get the root mean square error. You get S hat. So this is S hat. As I told you, can be also called, I told it before, because when you estimated our last exercise, this can be called also standard error of the regression. So you see now, with only few information, we were able to compute everything. But you see that now, I know you are tired, you need to study, but you see how instructive it is to study a table like this, because you see, we review, we connected all the concepts. Obviously you are tired, but study. Now, last 2 minutes, I finish with the theory. If you don't have question on this, I close and I tell you only, I show only one thing, but I do not explain. I do not do exercises. So, or maybe I open the, as I told you, I upload, I repeat it again, and then I let you really to go, guys. I uploaded this morning, I told you, again, a folder with the same first H mock exams. You have to study, do them. They are without solution. I do not have the solution. Tomorrow, I will answer again to your question by doing exercises with you, taking from this one. I prefer to avoid exercises on the regression in which you have a lot of computation to avoid to lose time, but I explain if you have question, ask me however a question, I explain what kind of computation you have to do. Furthermore, yesterday I prepared these 2 new exam simulation. These are new because I repeat, I prepared them yesterday, and look what I did. Okay, here there are questions. I hope I wrote, I didn't do a lot of mistakes. And look, here I did 5, given a trivariate sample, xi, si, yi, with I equal to 1 to 60, the estimation of the model y equal to beta 0, beta xx plus beta 2s plus epsilon produced the estimate reported in the Excel file. What I want to tell you, this is an example of a bivariate regression. It is a multiple regression model in which you have 2 regressors, x and s. And now you should be able to do this exercise, because to do this exercise is similar to this one. It's shorter because here you have 5 regressors. Instead, I use 2 regressors. I called one x and the other s. And if you close for a moment here, we finished, guys. Okay, we finished. Here I prepared another one, and again a similar exercise. And look, and I really finished. I'm not explaining. So relax yourself. So open the file Excel. You have no solution. However, since I prepared yesterday, I invented the results, so I did the exercise yesterday, this one. Here I prepare the table, and here you have some information. You see, you have the sum of squares of the regression are the model that explains sum of squares and the total, and you have essentially a table similar to the one we completed together. Here, the estimate of the parameters of the model, but here a lot of question marks. You have to put the number inside the question mark. Analisi della varianza means, guys, variance analysis, which is another term to call sometimes the variance decomposition. And here, however, so here if you have troubles instead, you can compare the solution, because here there are really the solutions, so you can always verify. Okay, you have two file Excel, and you see this file Excel obviously is associated to this PDF, and this file Excel is associated to this one. Okay, guys, stop unless you have question, and tomorrow, as I told you, I will answer to your question by solving exercises taken from here. For this one, I told you study, because tomorrow is the last chance to make me question, and tomorrow for the 3 hours I will do the exercise that you require me to do. So if you have already asked me question, probably someone will ask them again, and I will spend maybe more time to explain again the answer, because tomorrow I will take open board, so I will write with you. Okay, and so look at the simulation. If you have troubles tomorrow, you can ask me. Okay, unless you want to ask me something already, you can do it, but otherwise, okay, do what you want. Otherwise, guys, you can go now, because I repeat, everything is uploaded in the chat, and maybe it's also among them teaching material, maybe already inside the teaching material. Okay, guys, so if you have question, otherwise you can go. Okay.
Thank you. Bye.
Thank you, guys. Thank you. Bye, guy. Bye. Bye, guys. If you have question, you can ask me. Okay, as always. Okay. Questions? So I don't see questions, so I think it's okay. I mean, tomorrow make me question, okay? Bye-bye. Oh, I need to stop the recording.